We will now continue with Mr. Labahn from the University of Rostock. He received his doctoral degree and finished his habilitation both in discrete mathematics and combinatorics. And he led various research projects for developing algorithms and technologies for handwritten text recognition based on state-of-the-art concepts of computational intelligence. And he will present to us key concepts for handwritten text recognition.
Yeah, first of all, I would also like to thank the organizers of this event, of the Co-op Convention, and of course of the READ kickoff meeting for giving me the opportunity to talk here. And in particular, I would like to thank Günter Mühlberger for inviting me and my group and the Rostock team to the READ project, and we are really proud of it, and we are looking forward to contribute hopefully to the success of this project. My talk will be completely different, and I warn you, this will be a technology talk. I'm really here, and also my colleagues who follow me today in the morning, to explain how we are doing the handwritten text recognition. And I believe, and I'm really convinced, that it is also necessary for people who want to apply these technologies for having little understanding in all the basic principles. My experience as a mathematician is, if you try to sort of dive into application projects, you need to learn to talk to people who can speak about the application, but also this is a sort of bilateral negotiation of all of this. And so the aim of my talk is, from one side, to explain these things a little bit, how we are doing it, but of course I'm not diving into all these details because these are hours and hours of mathematical presentation or computer science presentation here. And also I would like to set up the ground in a little sense for upcoming discussions. So I'm not really, hopefully everybody can understand me because I'm sort of moving here. Sort of setting the ground that we can talk to each other. And so some of the terms which come here will be on the slides are also important to make ourselves able to understand and to know what we are talking about. So it might be a little bit introductory in a sense that you learn our language. So if you follow me with that, then we're probably lucky on both sides at the very end. I'm not going to present too much results because I'm looking forward to these days here to having many, many more slides and pictures of handwritten text and maybe recognition results and so on. So this is really foundation. This is the concept of my talk here, of course. After a short introductory part, I try to meet the subject of my talk to point out what the concepts are in a sense. But this part of the concepts will also go through the talk. And then we in Rostock, in my place, in my group, focus on the recognition task. So this is the main part from the background here. And you cannot do this without having something which I call interpretation. We used to say decoding of the thing we did before, and then of course a little epilogue of So the introduction. Let me first put the whole thing into the workflow. With the workflow, I mean the workflow which is also the workflow of the READ project. I'm also going to describe our position here a little bit. And we are somehow, in a sense, responsible for one HDR engine. So HDR stands for this handwritten text recognition, of course. Our position is more that we assume that we are getting some writing images which we process. This might be lines, this might be words, but in the view of the main subject or one focus of this workshop, where we also have documents like cards and everything that might be table cells, for instance, or these document fields, form fields. So imagine just we have something which contains text. And in the following part of the talk, I will call this a writing. So a writing is somehow a piece of an image. And of course, everybody knows that this part of the writing, or to find this part of the writing, is a hard task. We have the talk of our colleague Basilios Gatos today for the hard task in the background. I must acknowledge over the years that this part, which we used to call in the last time layout analysis, to find text blocks, is much, much more important at the moment rather than reading. So I skipped this here, but still, it's not because I underestimate its importance, it's just because we have another talk of it. So then once we have the writing image, I explain the HDR engine, at least what we do with the HDR engine, and then we get out some textual information, that's what I call. And this is not just text. It might be text, so that we really want to know what's the text which is written there. It might also be something which is sort of position, for instance. We just heard that we are looking for keywords, looking for names, looking for dates and things like that. And so if we have the information about the position where this word is, then it's also worth keeping in mind that. So this I subsumize under the word textual information. And once again, it's not just one information, it's a whole lot of information. And that's also something which is, from the concept point of view, very important to understand, that we always try to give alternatives and that we at the same time really are forced to give confidences. I would really like to stick to the word confidence rather than probabilities. It's more because it can be a probability in the mathematical sense, but it's not really necessary that it is a probability. So if you understand confidences like probabilities, then why not? I will then stop with my part, in a sense, and not going to the application. And once again, it's of course we are aware of it and we are using it and we are dealing with application, but we have another talk of our colleague Enrique Vidal, who will afterwards speak about the application in this sense, the keyword search, which I put in front of here because it's just the next talk, but also of course the transcription of some documents and so on and so on. So my focus clearly is this part of the whole workflow, but as I put here, the READ project of course covers, even from this technology point of view, the entire workflow, not just the HDR engine or some part of it. My part here, or the part of the CITLab group in Rostock, is the HDR engine. And now let's magnify this a little bit. What's in here and what's the steps which we are dealing? These HDR machines can be seen from different point of view, and they certainly have different possibilities how to approach. There are, at least as far as I can see, 3 somehow different things which I should mention at least here, and also to make sure what I'm talking about. First of all, or maybe not first, but what I put here first is topological methods. So for instance, you can try to find the substructures of the writing which you see. You can try to detect what you put here, like arcs or lines or curves, holes, and so, and try to learn to read these things. At some point, I see this as a more like differential way of looking at the writing of the part what is written. It has the advantage that it is very fast, these methods, and it's a little bit dangerous because if you fail to see tiny little pieces at some point, you fail to read the whole thing. So it's everywhere. There is a trade-off, of course. I will not speak about these topological methods because I cannot do it, and it's also not really part of the READ engine as far as I know from this moment. But then for the HDR engine, we do have 2 different approaches, which also in the historical way, of course, have these 2 titles. The first one is HMM-based methods. The HMM stands for the hidden Markov models. And there is the engine which is in the Transcriptorium project, of course. I will only briefly mention that the basic idea is that you traverse the writing from left to right, let's say, and that you keep in mind what you see and formulate or memorize these things in so-called states of some, what they call in computer science, automata. And then you estimate probabilities to going from one state to the other and so on and so on. And I will not talk about this topic because the real specialists are here again. The specialists are friends from Valencia, the real specialists in the hidden Markov models. And so that's a topic which is important, but not the topic of the Rostock group, which came in the last years into the game. And these methods I would entitle like RNN-based methods, where the RNN stands for recurrent neural networks. And that's the part which we try to introduce in the READ project, so having an alternative engine and an alternative method and also workflow maybe for getting results in the sense that I described before. Okay, so let's dive into the details of this. The whole recognition procedure has several steps. And these steps are also of different importance for my talk, but I should summarize it. On the left-hand side, you see more like the processes, and on the right-hand side, I, in parallel, depicted a little bit what the data is, what we are handling there. So first of all, what we are doing is, imagine we get these writing images, we put some pre-processing. This is not the pre-processing, what I used to call image pre-processing, which we saw before. You look at your scans and try to recalculate the image, sharpen it, or make the background things, and so on. It is a normalization or also corrections of the handwriting itself. So you all know that people write with different slants, that you have different heights in the words, and so on. And we try to find some standardized writing which has a fixed baseline, which is like a horizontal fixed slant, which is more or less what we define, and so on and so on. The main thing here is not to make this or to make this writing so that we can read it as a human as good as possible. That's not the idea. That's not important. The important thing is to make these writings so that they meet the world of writings our machine, our engine has seen before. So that's very important to understand. What we as humans like to see in terms of writings, in terms of data or whatever, is not important anymore. The machine is the thing we are focusing on. And so it's more abstract things. If we decide to put every writing top down or as a mirror image or with a slant like minus 45 degrees or something, that's fine, as long as we do it all the time. Yeah. I'm not really speaking about this writing pre-processing anymore, but we have a colleague here from my group, so we are 3 from Rostock here, and one of the persons, I show you the faces at the end of the talk, you can, he is really curious and eager to answer all your questions and discussions. I will focus on the recognition part. So the recognition part now gets an image which in a sense is a standard. And this image contains a writing which is standard. That's better what I should say. And now it tries to extract the recognition information from the image information. That's the main part of this recognition and the main part of my talk. I will dive into this in the next part. And then we go into the decoding part. And the decoding now means to get this information, which so far is just mathematics, is just numbers in a matrix, let's say, what we call, let's say, a recognition matrix for this part of the talk. To transfer these things into what I announced like textual information, textual output. So the interpretation in words, for instance, or in dates or whatever we try. And this is also the part where we put in more knowledge, which we may have or at some point may not have, which comes from the external side. Like, for instance, we may have dictionaries where we know that, like, I don't know, for the Venice Time Machine, we know the list of names which have to be expected in Venice or something like that. And so we can restrict our expectation to something which we know in advance. Also here language models come in, and so on and so on. Please understand that this part in the middle is completely independent of whatever language we want to have. One question which is always to be discussed is language independent? Well, in the classical human language sense, yes. Yeah, we put in language maybe here, but this part is completely independent of language and many more things. Okay, let's go. So this is the basic shape. Now let's go into the concept part. We start from the classical OCR. The classical OCR is thing which we meet everywhere here, and everybody knows the word optical character recognition stems from the fact that we have a sub-image of the whole image, and this is sort of per character. I picked an example image, and the name Bad Doberan, it's a city a little west of our city Rostock, one of the first German seaside resorts, where the Mecklenburg dukes, even at the end of the 18th century, started seaside resorts there. And also on one of the cards we saw, which have been collected in advance to this convention here, we saw on one of these cards the city name of Bad Doberan. So it appears. And as you can see here, of course, this having sub-images per character, at one time it's a demand, we need it, but on the other hand side, it's very difficult. Like this segment here, you cannot say what's on letter, right? It's impossible. It's basically impossible. So one of the major things to understand is that now we are switching to what we call segmentation-free reading. So we are processing the entire scanning, the entire writing like more in the sense of a data flow. So these images, as I said, may be words, but it also may be lines or blocks of text. And these blocks of text are now considered to be one piece, maybe even a page, I don't know. But mostly at the moment, at least with these examples, we work on the level of words or lines or what these table cells, for instance, are. So how can we imagine this? Like this. We have, let's say, a little window, and now imagine this window slides over the image, and in every position, the machine now says, okay, I believe I see a B. Or here I believe I see a B again. There must not be one B, but it's a sequence of letters now which come. Here, basically, the machine may not know what it is, and so I depict this very special thing by a dot. It's a special thing which appears throughout my talk. The dot really means I don't know, and I have to put it into somehow into the backlog, and let's see what happens. We come to this later, because if now you switch this frame to the next one, you see an A. You wouldn't probably believe me that we see an A right here, because if you just only look through the blue one, then it might be basically everything, not just the A. But this comes also to, here we also see my next topic. If you now consider the data flow, the stream of data here, of both together, one after the other, then you can imagine that the machine has an idea, having seen an A, if it has or keeps the experience of what it has seen before. So let's see it sees a D here, or this is the symbol for an empty space here, because it's two words. It doesn't matter that these are two physical words. Remember what I said? It's not important what we humans see, that Bart is a word and Doberan is a word. It's not important. We have it, by whatever reason, as one writing, right? So we see this empty space. Now then we see again, maybe what put I here, a question mark. In a sense, I don't know, but then I learned that's a D. Next important concept is that there's absolutely no need to do it from left to right. Once again, we humans read from left to right. Arabian language and many more others from right to left, of course. So we can do the same thing the other way around. And we keep information also walking through the writing in the other direction. If you observe yourself in reading, then you know that it's also important at some times to having read the end of the word before you detect what was written in the middle, if it's really strange, right? We also do it back and forth. So what we are now doing, we are doing our scanning procedure. I do not mean the scanning in a scanner sense, right? This scanning over the writing, that's what I mean now, in various directions. So, for example, from left to right, and there will be more, from right to left, of course, also. This is image context. The other one here is what I already mentioned. Image context is important. Just a small illustration, because it appears then in my result page, exactly this one. If I cover this part of the word, you wouldn't be able to really detect whether this is an N, like in Batovaran really appeared, or an U, for instance, right? We'll mostly see an U here. This one is even completely not explainable, at least not with a certain security or certain probability. So we need this context I just described, yeah? Also what we need is language context. Well, language in a sense that it comes into the game in this decoding part, right? If I ask you for what we call free reading tasks, there's no restriction to everything, we can read any word, then probably my machine will not be able to find the Bad Doberan here, really, and I put something which I saw in some experiment. Really some letters which could mean everything in a sense, right? If, in contrary, I restrict to something which gives me external information, I subsumize this under the language context now here for the slide, then of course I will come up with a perfect result here, Bad Doberan. If, for instance, I say, okay, read a German city name, and I give the list of these city names. Or if I even put the keyword search task, find the name, where can you find the name Bad Doberan? Then I'm pretty sure that our machine will find this Bad Doberan as a really real result. So what really makes sense is, and is a concept of all of this, is not to ask what is written there, because we absolutely don't know, at least not for sure. The question is, what is the optimal, or in the keyword search case, a possible correspondence between the writing-reading result, which we had before, and, for instance, this dictionary entry or a keyword. So all I'm talking about is about probability. What can it be? And it was a big surprise even for us to see what a huge lot more of information has been or is hidden in the recognition result if you approach this with a more sloppy approach, asking what could it be. Try to find also the hidden results, not just ask for the one transcription on the top of everything. So, at least for me, this was very important to understand and to get into these conceptual new ways, in a sense. So we started with the OCR and put new paradigms, new concepts on it, and this, of course, puts the question whether we should use a new term. And that's, for me, an important thing to notice also in this audience, that we here in the read context said, okay, we call this the handwritten text recognition in comparison to the old, OCR, like character recognition. Some people talk about automatic text recognition, and since all these things are under development, I'm sure there are different names for it. But the main thing is to keep in mind that there is a new extended concept compared to the old OCR approach behind the whole scene. We are not heading for single characters. That's everything, right? Okay, let's a little bit dive into the recognition procedure itself. The recognition itself consists of, I would say three phases in a sense, or aspects. First of all, we try to extract what we call features. I will very briefly show you how this works because it somehow reflects the scanning approach again. Then I'll explain how we process the entire writing. So what we feed into the machine is now the entire writing, what happens there. I explain the neural network, which we use very roughly, of course. And then the training aspect, because it's very important to understand and also very important for the application. So feature extraction. We could work with the original image. For simplicity, I put here a gray image, which I had all the time with Badovaran. But, as usual, we have to transform these things into numbers. And apart from just taking the gray values, which is possible, which you can do, you can also try to make these things a little more smooth by taking averages. And usually what is done is a so-called filtering. So we put a filter here. I just picked a 4 times 4 square, and we build up some average over these 16 gray values. It's a weight average. So in a sense, you can say, okay, the left upper corner counts less than the corner than the middle pixels or something like that. So imagine we now calculate such an average and take this as the input. And now we are doing it with the next frame or with the next filter, let's say. And if you observe it carefully, you see that I put here some non-empty intersection. One of these rows here is taken twice. And that's usually what we do. You put these filter shapes, and you may intersect or may not intersect, may have more overlap or less overlap. At least the important thing is that now you're scanning your image and building up these averages, for instance, like I did here, from top to down, and then from left to right. But there's, again, no need to do it or no force for doing it like this. You can always do it the other way around. So, for instance, you can do it from the low right corner to the top left corner like this. And again, these other two directions also. So that's what I also mean with scanning. Now imagine we scan our images in very different or in various different directions. And the idea is to keep in mind, to memorize somehow the information, what happened in the writing, and memorize what was left of what I'm looking now at and what was right. And to glue together all this information from any side. And this gives a huge lot of more of possibilities for the recognition. Okay, so we are actually working with 4 scanning directions, and now I depicted it briefly like this, but you understand that the blue arrows here mean working from left to right and top down, for instance, and so on. And we collect all these data, and if you put these data into a sequence, then you get a you get a flow of data coming in. And this can be interpreted as signals. And so we are speaking very much and very often about signals which are coming in and what they are doing with a signal. So signal is just the flow of data coming in while scanning the filtered values of those such images. Now you have to memorize these things to keep in mind what happened before, and before means to the left top, to the left lower left, and so on, all directions. And this is done with a neural network. The neural network has a complicated structure, and I'll show you two levels. The neural network has a lot of cells, which people call neurons. People imagine and believe that it is somehow a little bit like our brain, it works like our brain. And what makes these cells being able to memorize information are recurrent connections. That's the point for having memory. So not just reading the next part of the image, but also keeping information by recurrent connections which I had before. Keeping information which I had before is the idea. So usually every mathematical talk has to contain a formula. I refuse to do it here, and my colleagues will probably blame me for that. And this is the substitute for a formula. Actually, this is cell people who are used to read these things in signal processing, for instance, know what it is, but everybody has an idea. Here we add up values, here we multiply, here they are somehow integrated, squeezed, or whatever. We also have the specialist for these cells here. This actually is a cell which is not used in Rostock anymore. It's the first so-called LSTM cell by those guys, Jürgen Schmidt, Huber, and Alex Graves, who invented the whole story here. So the basics, the foundation has not been invented in Rostock. We are using some more stable and more advanced cell. And if you are curious what these things are, so you ask my other young colleague, which we have here in Marburg. He is also can also show you more interesting pictures. So what is interesting here? First of all, I show you the recurrent connections. So these cells are such that if you start out with a certain value here, then you feed in the same value to the cell itself, or you take this value and feed it to the cell itself. So that's first aspect of recurrency. The second aspect of recurrency comes in these more global network structure. We now start to put these cells together in layers. This is a layer with many, many cells. I come back to statistics immediately. And then we stack around one on top of the other, and we build up a so-called hierarchical network. There is a lot of possibilities how many these are and how many layers, how many neurons, and so on and so on. And finally, we end up with a result on top in the output layer. And so we are sort of working or putting the image signals through the network, getting the information on the other end. That's a picture which I took from the original Schmidt-Huber-Graves paper, where you can see that we also proceed or can process, let's say, like here, Arabic names. I don't know what it means, and we had a whole project with these Arabic things. It's completely independent from right to left, left to right, and I guess you have now an idea why it is the case, from the letters and so on. So the low-level features look pretty much like what we can read again. On top, I guess you have an impression, on top here, top left corner, it's just figures. It's just something. You have, as a human, you cannot read it, right? It's just a little something of numbers which ends up in the network. And on the final level, I come to this later, we have neurons that say, okay, I might see a letter D, or I might see a letter B, or something like this. Yeah? So that's the principle of these neural networks. Now, the crucial thing is to train these networks. What can we train? Parameters. You haven't seen parameters so far. Maybe I go back to the slides I had before, like maybe this one. Imagine if I would add up numbers here. I have some input from somewhere and try to add these numbers, then I can put what we call coefficients, parameters on it. So what usually is drawn, I have not done it here to make it not too complicated, is that every of these edges carries something which we call weight. Which it's a factor, it's a little summoned something which has to be tuned, and with the help of these so-called weights, we can make or build a network which is able to work for a certain task. The objective of all of this, mathematically, is to optimally adapt these parameters in the cells and also in network connections. And how to optimize the idea of machine learning is to train these networks with data samples and minimize the error. And error is something when we have training data, we have training data where we know what we call a target, So we know what it really is. We know the text which is in the image, for instance, and then we measure the distance between what the network says and what the target is. And now try to minimize it. I'm not going into the details. It's another, months of mathematical lectures. More practical impression on this. We are currently working in a large but realistic application case on ordinary machines with 10 to the 4, so 10,000 network cells, 1 million trainable parameters of these networks, the learning data samples, so writing images, which we have here at some point is 10 to the 4th, 10,000. And then these things are fed into the network over and over again to make the parameters tuned better and better and better, 150 times. And if you train such a network from the scratch, then the bad news is that it might take 4 weeks. We try actually at the moment to apply more advanced mathematical methods to make it faster and to make it more precise and bring it on more parallel machines and so on. There's a lot of effort going on. But still, this is an essential task, to train the network. The good news is that we can support you. And I guess it's now something like the commercial break in the technology talk for the READ project, because now we want to set up some system with READ, at least that's also my understanding, that we try to support this process of having this learning data and bringing the networks up to life. So the labeled training data samples, some point we also speak about the ground truth, is writing images with correct text, and READ is the environment where you can work with these things. Of course, it's better to have more of these data, but the good thing is if you can start with a realistic number, you might be able to improve your result while working. You'll start when you have a reasonable number of learning data and try to improve. Do not expect that we have a network ready to use for any project. It's certainly not the case. And your learning data should represent all the data you have. But on the other hand, other people also have similar writings, right? Writing styles, writers, and so on. So you can maybe start with an HDR network from similar collections. If you're using READ, this is one of the ideas, to have a sort of zoo of networks ready to use for a beginning, and then maybe a little bit adapting to your particular task. So the hope of all of this is that the crucial point of having so many learning data and having such an elaborated and advanced training can, in a community, be made easier and more attractive. Okay, a little word in my last minutes to the interpretation and decoding. So far I did not tell you what the world is when we have to retranslate these things to our understandable language. So what we always assume is that we have abstract characters, so abstract letters. These might be our letters which we have, like digits, for instance, in my example, which follows immediately, uppercase, lowercase letters, special letters like here these blanks or so. But you have only to make sure that your text contains all these letters and the text has been made from these letters. These alphabet characters are the output neurons, and we also say these are channels of the network. So if you talk to my colleagues, then we'll always speak about channels. The whole concept is much more general. You can put any symbolic unit which you want to learn into a channel. So, for instance, if you want to have different styles of writing, put it in a separate channel. If you have a medieval text, I don't know, they had hundreds of letters, for instance, not just these few letters we have today, of course. That's something you know much better than me. In our large application case, we work with 150 character channels. It might be more. It's not really tested what is the maximum. I'm always speaking about usual university machines, not very fancy Google type of cluster things or so. Certainly it's independent, but I said this from the natural language, from the reading-writing direction, from the understanding, which is very important to know, that we always measure the probability at a channel, a probability that a certain character appears at a certain channel in the writing. So, and my final slides now just depict these things for the Bateau-Baran, for instance. If you now imagine you have the Bateau-Baran here, and the darker it is, the higher the probability. then you have an idea that these neurons say, okay, here's a B, and so on through the scheme. And the schemes are built up by probabilities, so you can also find different ways through the whole thing. And these different things are depicted in this picture a little bit. So that's the output matrix I spoke to you, or I announced before. And you can find different paths through this output matrix, which then tells you different possibilities of what the reading might be. Okay, final image, which I am grateful to my colleagues from Valencia for bringing it together. We have more of these images, and if we talk to each other, we can, of course, show you some reading results. And that's the last slide. I should always mention that we as a whole group in Rostock and two colleagues we have here, these two faces are the ones you should look for if you want to talk to them about these topics. I also have to thank my partner, our MOU partner is the Planet, a small enterprise, which does all this work together with us, and of course the EU for funding, and the audience for your patience and attention. Thank you very much.